Bismillahirrahmanirrahim. Chapter number 6, Fluid Mechanics. Today we are going to do numerical number 8. The statement of numerical number 8 is a hole is drilled at the bottom of a full bucket of water of height h. What will be the velocity of water that exits from the hole? Basically, we are given a bucket which has a depth of height of h, and there is a hole at the bottom. That means the depth in this case will also be h. According to the given data, depth of hole is equals to h. We have to find speed of efflux, that is v, and the formula that we will use for this purpose is Bernoulli's equation, that is P1 minus P2 is equals to half rho V2 square minus V1 square plus rho G H2 minus H1. For solution, firstly we will rewrite the Bernoulli's equation, and for substituting the values in this equation we need to know some values. Number one is the pressure acting on upper side and on the bottom is atmospheric pressure, that can be represented by P, as at both ends there is the atmospheric pressure acting, so we can call P1 is equals to P and P2 is equals to P. Similarly, at the top end, the velocity, as the area of cross section is very large, that's why their velocity will be very small. So we can neglect V1 as compared to that of V2, which will be very large. According to equation of continuity, we know that whenever there is a larger area, the velocity gets very small. So the upper cross sectional area is very large as compared to that of the hole at the bottom. So we can neglect V1 in comparison to V2, and let us consider that V2 is equals to V. Similarly, you have given again that the depth of bucket is h, which is equals to h1 minus h2. So now, since depth of hole is equals to h1 minus h2 is equals to h, for our formula we have to substitute the value of h2 minus h1, which will be equals to minus h, because I have taken minus common from this equation and taken it to the right hand side of the equation. Hence h2 minus h1 is equals to minus h, and v1 is so small that it can be neglected. Let v2 is equals to v, p1 is equals to p2 is equals to p is equals to atmospheric pressure. Now substituting the values in the formula, P1, P2 both are P. Similarly, V1 square is equals to 0. That's why we have not written it over here, and in place of H2 minus H1 is minus H. P minus P is 0, and plus minus will get minus, so we have minus in this equation. Now we will take this to the left hand side. We will get this result, and cancelling rho and rearranging we have V2 square. Basically 2 will get multiplied over here, rows will get cancelled, and we will have the result V2 square is equals to 2gh. In order to get the value of V2, that is the speed through which the water will flow through the bottom of the bucket, will be V2 is equals to under root 2gh, which is our final result. Now, similar to that of numerical number 8 is numerical number 9, the statement of which is the efflux speed of an oil from a narrow hole of tank is 33.8 meter per second at a pressure of 4.12 into 10 raised power 5 Pascal. Calculate the density of oil. Given data is efflux speed, which is 33.8 meter per second, and pressure through which the water is the oil is coming out of the hole is 4.12 into 10 raised power 5 Pascal. We have to find the density of oil, which is rho. The formula that we can use for this purpose is Torricelli's theorem, according to which V is equals to under root 2gh, which we have just determined in numerical number 8. So for solution, V is equals to under root 2gh, but we have not given the value of h, we just know the value of 2 and g and v. Meanwhile, we don't have to find the value of h, we have to find density. So we will convert this formula in another formula which will give us density. And we know that pressure is equals to rho GH. From here we can rearrange and we can find the value of GH is equals to P by rho. So in place of GH we can put the value in equation 1, which will become V is equals to 2P by rho. Now we can determine rho from here, because pressure is given to us, velocity is given to us, we can easily determine rho. You can substitute the values here and rearrange them to get the answer, or if you want to firstly rearrange the formula and then substitute the value, then you have to take square on both sides. V square will be equals to 2P by rho, and V square is equals to 2P by rho. Putting values in it, we will get 33.8 square is equals to 2 into 4.12 into 10 raised per 5 divided by rho. Rearranging, we will have this result of rho is equals to 721.263 kilogram per meter cube. The answer given in your book is 0.721. That is basically kilogram per liters. So if you want to convert this result into kilogram per liter, you just have to divide this answer by 1000. Otherwise the standard unit is kilogram per meter cube. So I have taken the answer till here. Also, I want to tell you that you can directly use the formula by using Bernoulli. You can write the answer that according to Bernoulli's equation, P is equals to half rho V square, and instead of doing all the derivation that we have done in the last page like this, you can directly use the formula P is equals to half rho V square to get the result of density as 721.263 kilogram per meter cube.